Hello and welcome. In this video, we will be using PyMol 3 to generate and save publication-worthy images. By the end of the tutorial, you'll be able to understand the differences between saving images and ray tracing, use scenes to save views, add and move labels, and use a couple of different ray tracing settings to create beautiful images. Let's get started. So we're here in PyMol 3, and if you're following along, go ahead and find the SLES bilayer PDB file in the PyMol 3 course data directory and use the File Open menu or the Load command to bring this into our PyMol session. Here we have a sodium lauryl ether sulfate, or SLES, bilayer. SLES is an ionic detergent and surfactant which is used in many consumer packaged goods, such as soaps and shampoos. This bilayer was built using the Schrödinger Materials Science Suite, and you can learn more about this example and workflows relating to surfactant tilt and electrostatic potential in our Molecular Modeling for Materials Science Applications Consumer Packaged Goods Schrödinger Online Certification course. Most surfactants are organic compounds with hydrophilic heads and hydrophobic tails. The heads of surfactants are polar and sometimes carry an electrical charge, and we can see that the lauryl ether sulfate molecules here have the ionic or negatively charged head groups and then these hydrophobic tails. We can also see a number of sodium cations represented as purple spheres, which carry a positive charge, and water molecules. This is a liquid mixture that has undergone a molecular dynamics simulation, and a bilayer has formed as all of the charged atoms and polar water molecules are in close proximity as they're forming favourable interactions here, and the lauryl ether tails are also aligned as they're non-polar. As we've seen in previous tutorials, in some cases it can be really important to show off all atoms, and in other cases we might want to simplify the visual representation to better convey the science. In the Hide submenu, find hydrogens and then non-polar. You are welcome to play around a little more with the representations, try out some presets, display the polar interactions, and edit the colours to your liking. Once you're happy with how things look, we're going to save this image. In the panel toolbar, click on the Draw Ray button. Here we can edit the dimensions and pixel density or quality of our image. For now, let's keep the default settings and click Draw. The Draw option captures the image exactly as you see it on the screen, albeit with the chosen size and resolution properties. We can choose to save this image or copy it to clipboard to paste elsewhere. I'm going to save this as SLES image default, and the file type here will be PNG. If you accidentally click away, the save option will still be there. Opening up this image, we can see it looks fine, basically like taking a screenshot of whatever we can see in the PyMol workspace. And that can be useful, but we can do a whole lot more with the ray option. Let's try out the default ray tracing settings and compare the output to the image created using the Draw option. In the Draw Ray panel, click Ray, and depending on your system size and the complexity of what's being displayed, this will take a couple of seconds longer than the instantaneous draw option. We can see a loading bar and an abort button appear while the image is being ray traced, and the total capture time is reported in the command log once the rendering is complete. We can see the final version in the workspace now, and we have the option to save as we did with Draw. I'm calling this one SLES Ray Default. Side by side, we can see that this image gives us overall higher rendering quality, and we can see some nice lighting and shadows in the ray traced image. Another really nice feature with ray tracing is that we can render the image with varying layers of transparency, for example using clipping planes to indicate depth, or to overlay different representations such as semi-transparent surfaces. Having these alpha channel options means we can even check the box to enable a fully transparent background when ray tracing. Transparency can be really impactful when creating images for publications, or even if you simply want to add an image to a presentation or a poster that has a different background colour. And speaking of printed media such as posters, we can set the colour space via the display menu and the quality and size based on pixels, centimetres or inches. For example, we can easily modify these settings if we know we want our image to be 10 centimeters tall on a poster printed at 300 dots per inch using the CMYK color space. There are a vast number of ray tracing settings that can be customized within PyMol, and you can learn more about them in the PyMol command help, the PyMol wiki, and by trying out a number of the different settings that are available in the display menu. We will be getting into using scenes for movie making in later tutorials, but we can use them for static image creation too, if we find a view we like or if we want to be able to recreate a ray traced image at a later date. Click on Scenes in the panel toolbar. Click on the plus icon in the blank box to save the current view in the workspace as a scene. Zoom in and change the orientation of the object and save another scene. Now click on the original scene to be transported back to this view. Pretty nice, right? Have a go at making some edits, saving new scenes, and ray tracing the different views here. Be aware that the more complex your settings and the larger your system, the longer your image may take to ray trace. Next, let's take a look at a structure where it might make sense to include some labels, for example the distances between atoms that are likely to have polar interactions. I'm going to load in an example from an earlier video here, but you are welcome to simply fetch the 5IEY structure and apply the ligand sites cartoon preset to create something similar if you like. A reminder that we can display labels for interaction type objects such as our polar contacts using the object-specific S submenu and choose to show labels. We can now see the distance in angstroms between all of our polar contacts. This would make a compelling image, so let's ray trace this. It looks good, but it could be better. The label colour is white as we currently have a black background, but with a transparent background these white numbers are a little hard to see. Let's use Display Background White to change this. In the workspace, and ray tracing this again, we can see that the labels are now rendered as black text. This looks better, but let's rotate and zoom in a little to create a nicer view so that the key sidechains and interactions are displayed. Save this as a new scene. Now let's move some of these labels so they're not overlapping. Before we make any edits, let's save this session, as it can be pretty easy to accidentally move parts of the protein while in editing mode, and we don't want to do that. Okay, saved. Click on the mouse mode toggle to go from 3-button viewing to 3-button editing mode. Now, using the Command or Shift key, carefully select one of the labels and move it slightly so that it is more visible and no longer overlapping with the dotted lines. If you accidentally move some of the protein, the command log will tell you, and you can use the undo button in the action toolbar or Command or Control and Z on your keyboard. Phew! Okay, back to editing these labels so they look nice. And once we're done, we need to be sure to toggle the mouse mode back to viewing so that we don't make any accidental edits. And now let's ray trace this again. Beautiful! To take things a step further, you can show and edit the labels for key residues in your binding pocket here. Have a go at recreating a selection for just the residues that are forming polar interactions with the ligand and edit the positions of these labels. So far, our images look pretty nice, but we can take this up a level by editing some of the settings such as lighting, depth cues, shadows, and using different ray trace modes. Setting the ray trace mode variable in PyMol changes the way structures are rendered during ray tracing. We can't see the full extent of these different modes prior to ray tracing, but they provide styling that we can combine with other settings. Be aware that changing ray tracing modes or settings are global rather than object-specific changes. And be sure to save your session before typing any of the following commands. In the command input area, type set ray_trace_mode, 1. Now let's come up and ray trace this using the Draw Ray button. Or you can simply type ray in the command input area. Let's save this image as 5IEY RTM1.png to indicate we've used Ray Trace Mode 1. And repeat this process with Ray Trace Mode 2 and Ray Trace Mode 3. As well as ray tracing an image using the ray command, you can also save an image from the command input area using the save command or the PNG command. And with PNG, you can set the dots per inch. See the PyMol command help for more information here. We can see that with Ray Trace Mode 2, we only get a black and white image or an outline if using a transparent background. So this looks like a colouring book image or sketch. Pretty nice. And Ray Trace Mode 3 gives more of a comic book quantized or block colouring effect. Very cool. We can even set Ray Trace Colour to change the outline colour for Ray Trace Modes 1, 2 and 3. And this also sets the colour for labels. We can use a known colour or even a hex code here, for example Ray Trace Colour Magenta or Ray Trace Colour 0x00FFFF for cyan lines and labels. See the Ray Trace Mode reference on the PyMol wiki for more guidance here. Let's finish off this tutorial with some optional extra tasks that use session files from previous Visualizing Science with PyMol 3 videos. First, open the pdb101.pse session file that we used in the very first video of this series. If you open the Scenes panel, you will see a zoomed and centered scene for each structure in this session. Now that we've got a feel for how to change some settings with commands, let's revert back to the default Ray Trace Mode 0 and apply a surface to the 5ET3 structure, or the second scene. I'm using this as an example as the peptide or protein component is on the smaller side here, and ray tracing high quality surfaces for larger structures can be time consuming. A reminder that you can check out the PDB 101 article and the 5ET3 PDB entry to learn more about this structure and how proteins can direct self-assembly of superstructures like the sphere that we can see here. Ray tracing this, we can see that the shadows are somewhat distracting. For surfaces, it can be useful to turn them off, so let's do set ray_shadow, 0. Nice. We might also want to turn off the depth Q or fogging, and we can do this with set ray trace fog 0, set depth Q 0, or using the file display menu depth Q fogging. There are a lot of surface settings that we can alter, and you can learn more on the PyMol wiki, but let's do set surface quality 2. We can see this gives more detail, though now the elemental colouring doesn't look great. Let's set a uniform surface colour with the set command, surface colour and grey. Let's take away some of the reflective shine by doing set light count 0 or by turning off the specular reflections in the display menu to give this a matte appearance. Conversely, if you want more shine, feel free to go ahead and increase the light count. For example, here it's set to 4. One more thing we can do here is set the transparency of the surface. Let's do set transparency 0.3, where 1 would be fully transparent and 0 would be fully opaque. And now we can see the helices beneath the surface. I'm going to turn that light count back to 0 and set ray trace mode 1. And this looks pretty fun with a white outline. Notice how the outline is only applied to opaque representations here, like the cartoon and licorice, and not the semi-transparent surface. We've experimented with some fun settings manually, but another great tool can be found in the plugin menu. If we come up to plugin and choose lighting settings, we can easily choose some really nice pre-configured settings and play around with the sliders here. Finally, in the previous video, we created a new QtMol-like preset using PyMol 3's new presets panel. Here we applied some settings that really nicely demonstrate the differences between a drawn image and a ray traced image. Either open your preset session file and have a go at ray tracing this image, or if you prefer, import your custom QtMol-like preset so that you can apply it to the structures in your current project. Don't forget to save first, as applying presets from this panel means the changes are global, and it might take a minute to be applied in the PDB 101 session since there are a lot of big objects in here. Going back to our previous session, the SLES bilayer we use looks pretty great where we ray trace it with the QtMol-like preset applied. A considerable difference from the draw image that we created back at the start. Take some time to test out some of the ray tracing settings and have a go at creating some beautiful ray traced images for each of the structures in your previous sessions. And don't forget to tag us in your PyMol 3 images and movies on the Schrödinger socials, which are at Schrödinger.inc on Instagram and at Schrödinger on LinkedIn. That brings us to the end of this tutorial. You can now understand the differences between saving images and ray tracing, use scenes to save views, add and move labels, and use a couple of different ray tracing settings to create beautiful images. Thanks for watching.